In chapters 3 and 4, we focused on solid phase reactions, solution phase reactions. In this chapter, we're going to focus on gaseous phase reactions. We talked earlier on in chapters 1 and 2 about what a gas is, and we said gas is defined as any substance that has mass, takes up space, or that's matter, is any substance that has mass, takes up space. Gas is any substance that has no definite shape and no definite volume. There are several principles about gases that we learn to deal with throughout this chapter. First off, gases can exist for a lot of different materials. Some things exist naturally as a gas, some things don't. The substances that exist naturally as a gas are truly gases. For example, hydrogen exists at room temperature or at STP, standard temperature and pressure, which is defined as 0 degrees Celsius and 1 atmosphere of pressure. Most of the time we are dealing around those situations in a chemistry lab. Throughout this chapter, we'll talk about STP and we'll talk about reactions taking place at STP. It's a defined set of conditions. Anyhow, hydrogen is a gas naturally at those conditions. Substances that are not normally gases at those conditions but can be changed to a gas, for example, water changed to steam, alcohol changed to alcohol vapor, things like that, are substances that are not called gases, they are called vapors. There is a difference between vapors and gas, although we hear them used interchangeably. Under those conditions, all gases have a set of conditions. Here are the 4 conditions. 1, they will assume the shape and volume of the container they're in. 2, they are the most compressible state of matter. Compressible meaning you can squeeze them down into a very small space. 3, they will always form a homogeneous mixture. We talked about homogeneous mixtures earlier on. We said a homogeneous mixture is a mixture in which everything is blended together evenly. This one's extremely important to us because without this one being true, we would not have the air we breathe. We'd have to run around and look for oxygen pockets to find because the air were not homogeneous. All gases are homogeneous. It's not true of solids and liquids, but for gases it is. 4, they have much lower densities than solids and liquids. All right? For that reason, we'll find throughout this chapter that we don't measure their densities in grams per milliliter, we measure them in grams per liter. All right, so now that we've talked about what gases are, let's look at the properties that we measure with a gas. Again, let's compare it to solid-liquid phase. In the solid phase, generally we made measurements that was in the grams of matter. So we used the general property of grams as most of our properties. In liquids or in solution phase, we can still use grams when we're talking about making a solution, but for the most part we talk about volume and molarity as our measuring numbers. In gases, there are 3 main properties that we measure: temperature, volume, and pressure. Temperature and volume are pretty familiar to you, and most of you, if you've had physics, pressure should be as well. Pressure is defined as a force divided by an area. There are 2 ways you can increase pressure. You can increase the amount of force that the gas is pushing at, or you can decrease the amount of area it's flying to. Let me give you an example that you understand. We've all played with a garden hose probably at some point or another, and if you turn the water on the garden hose, just let it run out of the hose. It has a certain amount of pressure. There are 2 ways we can increase the pressure of that gas. We could turn up the force of the water, make it go faster, or we can put our thumb over half the opening, thereby decreasing the area that it's coming out of and increase the pressure. Gases all have pressure affected to them. Now, in chemistry, the unit we use is called the atmosphere, or ATMs. ATMs is the preferred unit of pressure, and throughout the course, when you measure in pressure or using a pressure in an equation, you must use atmospheres. Therefore, you may have to convert from some other unit to atmospheres. Temperature throughout this course must be measured in Kelvin. In Chapter 2, we talked about converting to Kelvin temperatures from Fahrenheit and Celsius. So again, make sure you can convert to Kelvin. And volume must be measured in liters. So throughout this course and all the equations you do, volume is in liters, temperature is in Kelvin, pressure must be in atmospheres. Now, how do you convert pressure? Is simply the same thing as doing dimensional analysis. The same as what happened whenever you would have taken feet and changed it to miles or something like that, or grams and changed it to ounces. It's just simple, straight dimensional analysis. In your book, there are 2 examples on page 177 and 178 showing you how you convert them. The first one simply asks you to convert 688 millimeters of mercury to atmospheres. This box right here gives you some general equivalencies. 1 atmosphere equals any of those numbers. 1 atmosphere equals 760 millimeters of mercury, 760 torr, 101.325 kPa, 1.01325 times 10 to the 5th pascals. In this problem, we're asked to convert atmospheres to, millimeters of mercury to atmospheres. So I find my relationship, and my relationship says there are 760 millimeters of mercury per 1 atmosphere. So 688 divided by 760 gets rid of millimeters of mercury, leaving me my units of atmospheres. And in this case, it would be 0.905 ATMs. If you'd like to look at another example on page 178, you can look at example 5.2, which again shows you another example of converting. But it's pretty straightforward dimensional analysis.